Okay, welcome back to Process Dynamics and Control. Today we're going to be talking about valve design. Now, valves are a common final control element for many control applications. It's the thing that we actually change in the process to achieve a control objective for chemical process control. Now, there are many different types of valves. For example, you can have a gate valve, you can have a globe valve, you could have an angle valve, a swing check, and also a disc type. So of all these valves, which one do you think would be a good choice for preventing flow from going one direction, but allow it to go another direction? So just looking at these different valves, we can see that a check valve, for example, would allow flow to go in one direction, but would close off as the flow tried to go the other direction. And also which valve is going to have the lowest loss, the lowest loss if we have it open most of the time. Okay, so maybe a disc valve, for example, may have a low loss. And there are going to be different types of valves that are going to be good for situations where we want very fine control of the flow and very accurate flow control. So different types of valves, different uses. These are just some cutaway views. So let's go on to, for example, a butterfly valve. Now, a butterfly valve is very good for on-off type control. When it's fully open, there's very low frictional loss within the valve, and we can achieve very low energy losses there due to the valve. But then it will close very quickly and shut off the flow. Okay. Now, if you had very fine control, you can imagine that as you close that valve just slightly, just closing it ever so slightly more, it's going to have very large change in the flow that goes through that valve. And so this one may not be the best valve for very fine-tuned control of a flow. But let's go over to a globe valve. Okay. I'm just going to show you the cutaway view of this, including the cage on this valve. And you can see a couple different things on this. This is a pneumatic valve, pneumatically actuated valve. And so we're using air pressure to change the valve position either up or down. Now, some valves have a valve positioner on it. So if you command it to be, for example, 40% open, it has a feedback loop within that valve to either raise or lower the valve stem to achieve 40% open, regardless of what's happening in the process. Okay, so these these valve positioners are much more accurate. They can control to a much finer tolerance the flow in a system. And I've got a globe valve here. I'm just going to pick it up. It's a little bit heavy, okay, there we go. So this is an example of a globe valve. You can see that the flow is going to come in this direction and then leave the other direction. We have a valve stem. Okay, so I'm just going to hold that up. And then we have a couple air pressure inlets, one on the top and one on the bottom. So instead of being actuated by or moving by a spring, you actually have air coming in from the top and the bottom. And this so this is one example of a valve. And you can see the cage is going to be down here, and this is the part of the valve positioner right here, the controls that go into that. Okay, so I'm just going to go ahead and set this down. And okay, so that is a globe valve, for example. Now, one of the things that we need to consider when designing a system is whether we want it to be fail open or fail closed. So if everything shuts down, all the pressure is lost that pneumatically actuates the valve, is this valve by default going to go to an open state or to a closed state? So one of the things that's important to consider is would it be better for the valve to remain open or remain closed? So for example, let's say you have a feed, a reactive feed to a reactor. And if the power shuts off on the plant, or there's some sort of failure, you'd rather have that valve for the feed to the reactor to close automatically. versus cooling water to a reactor. Let's say a nuclear reactor, you want that valve to fail open, okay? And so a valve that fails closed, then we have to apply air pressure to then open the valve. So that's called an air to open valve or fail closed type valve. If you have a fail open valve, then it's air to close it, okay? So it just depends on where the air is being input into the system. There's often a diaphragm, okay? So as we pressurize one side of that diaphragm, it's going to cause the valve stem to, in this case, to rise, okay? And then as the air pressure is lost, then the valve stem is going to close. So this valve, for example, is going to be a fail closed or air to open type valve. Okay, so let's just take a look at another one. Here is a one of these diaphragms with the spring actuator. Now the air is coming in from the top. Okay, so as you increase the air pressure in the top, then it's going to close the valve. Okay, so is this an air to open or air to close valve? Okay, so just think about that for a second. You know, is this, if I apply air pressure, does it open the valve or close the valve? And is it going to fail open or fail close? So you probably got it right. This one is an air to close or fail open type valve. Okay, so let's just go to a couple different valve designs. One of the things that we can choose is the geometry within the valve, and that influences some of the losses. So here we have a globe. You might have a split body or an angle type valve. Now, also when we talk about trim, we can have the same style, but we can change the trim in the valve. Okay, so that's how the valve, the stem is connected to this like a plunger that sits in the seat, and the shape of that is going to be the trim that goes into the valve and influences the lift versus flow characteristics of the valve. Okay, so a common type of valve that we use very frequently is actually called an equal percentage valve. Okay, now as we increase the lift by 1%, you get 1% more. So it's going to be a non-linear correlation between lift and the flow that we get, not attached to any process equipment, but just through the valve itself. There are also linear valves as well. So as you have additional lift, you get an equal fraction of flow through the valve. Okay, and so there's different kinds of trims that we can apply. Another one, for example, is a quick open valve. Okay, so if we have a little bit of lift, it's going to open very quickly. Okay, so you can see the the style of the trim that goes into that valve, but there are many other types of trim. Okay, so here, for example, is a parabolic. There's also quick opening, as we discussed. One of the things that you'll see quite frequently is a CV for a valve. Now CV is, it's going to go into an equation that we're going to use for the valve design, but it essentially is the constant that relates lift versus flow through the valve. Okay, for this table, what it shows is stem position or lift versus the body size. Okay, and different CV values. It's just an example, representative of some CVs for a particular type of valve. Okay, so a valve is going to be characterized by the CV value. So let's go on to the valve design equation. So here we have the Q, or the flow, is going to be equal to CV times a lift function. Now if that's a linear valve, that's just going to be F of L is just going to be lift. Okay, so that's going to be a linear valve. We're also going to be talking about equal percentage valves as well in this class, so linear or equal percentage valves. And then you also have the square root of a ratio here. Now this is the delta PV, so the delta pressure across the valve. Okay, that's the delta PV, and then the specific gravity of the fluid that's flowing through the valve. Okay, so that's in the denominator. So this is the valve design equation, and it relates the lift to the flow. And if we have constant pressure drop through the valve, then it's just going to be lift and flow that are going to be the two variables in that problem. Okay, so let's go to a chart now. So this is kind of a flow chart of this overall process of designing a valve, which valve to use for a particular application. So first thing that we want to consider is the safety. Do we want this thing to fail open or fail closed? And so that goes into like the cooling water versus reactants coming into the reactor. Okay, so that's the first thing to choose, which one we want. Then we want to calculate the the delta PV required, the pressure drop across the valve that's required, and that might be a function of Q as well. Okay, now the next thing we also want to consider is the design flow rate. Okay, so that's going to help us choose a particular type of valve. If we're designing the system to be very high flow rates or a wide range of flow rates, we're going to choose a different valve for each of those. Okay, so also we want to consider, does the pressure change for our system very much? Okay, so the delta pressure for our system, how much does that change with changes in flow rate? Okay, so if that changes a lot with changes in flow rate, then we're going to want to use an equal percentage valve. And with this equal percentage valve, it just changes that F of L function, and with an R value between typically 20 and 50. And then L is still the lift, but that's in the exponent of that function. So it's lift minus 1, so it's R to the lift minus 1. And so that would be your F of L in that design equation. So on the other hand, if the process pressure doesn't change very much with changes in flow, then we can select a linear valve. And the reason why we're going this yes-no route here is because we want the installed characteristic of our valve to be linear. Okay, so if we choose an equal percentage valve, then that means that we're going to get a linear response for the valve plus the system. Okay, but if the system doesn't really affect, the flow rate through the system doesn't really affect the pressure drop in the system, then we can choose a linear valve, because then the installed characteristic of both of those is going to be linear. Okay, so then as a final step, after we've chosen equal percentage or linear, then we want to go ahead and calculate the CV that we're going to need for our particular application. And typically we want the pressure drop across the valve to be a quarter to a third of the pressure drop across the system, the whole system. Okay, so we don't want it to be too much, because then we have to install larger pumps to compensate for all of this pressure drop across the valve, and also it helps us to maintain controllability of the flow. So we can either increase or decrease the flow as we increase, open, or close our valve. Okay, so then what we want to do as a final step is just go ahead and plot the Q, the flow rate, versus the lift, or L, of the combined system to check the linearity of this combined system, the system plus the valve. Okay, so that's the final thing that we want to take a look at, and we're just going to go through a brief application now, just to show an example application of how we do a valve design.